Exam review number 2, question number 10. The time it takes for customers to complete their shopping in a particular grocery store is normally distributed with a mean of 20 minutes and a standard deviation of 4 minutes. Determine the probability that a randomly selected customer takes more than 25 minutes to finish their shopping. So again, this is a normal distribution. So the first step, I'm going to create the curve. And the mean is 0 because I'm looking at the standard here. The question tells me determine the probability that a selected customer takes more than 25 minutes to finish their shopping. So 25 minutes is bigger than the mean because the mean is 20. It is here, so I will find the z-score that represents 25 minutes, and I would like to compute that probability because it says here more than 25, which means the area above. So the z-score for 25 minutes is equal to standardized 25, comma the mean, comma the standard deviation, which is going to be rounded to 4 decimals. It is actually going to be exact 1.25. So now to find the probability or the area greater than 1.25 when the z-score is more than 1.25, this is equal to, since I'm computing the area to the right, this is 1 minus the area to the left. Norm dot s dot distribution of 1.25 comma true, which is going to give me approximately 0.1057 or 10.57%. B, calculate the probability that it takes between 15 and 30 minutes for a customer to complete their shopping. So again, 15 is less than the mean, which is 20. So I will find z of 15, and then I will find z of 30. And I want the area in between. So I will find the z that corresponds to 15, which is equal to standardize 15, comma the mean, comma standard deviation. This is approximately, it is going to give me negative 1.25. Z of 30, or standardize into 30, you're going to get standardize 30, comma 20, comma 4, the standard deviation, and this is going to give me 2.5. So the area in between is going to be equal to norm dot s dot distribution of the bigger number, which is going to be 2.5 comma true, minus norm dot s dot distribution of the smaller number, which is negative 1.25 comma true. And this is going to give me approximately 0.8881, or in other words 88.81% of the time. Last but not least, C, what is the minimum amount of time it takes for a customer to complete their shopping if it happens faster than 90% of the time? Okay. So because it happens faster than 90% of the time, so the 90% has to be at the top. So this area right here must be the 90%. And that person that we're talking about is in the bottom 10% of the time. So you'd like to find this z sub x that separates the bottom 10%. So because the inverse function cannot use the 90% because it's to the right of the missing number, we have to use the 10%. So we're going to say that z is equal to norm dot s dot inverse of 10%, which is going to give me approximately negative 1.2816. Now, in order to find this specific time, which is x, we're going to use z sub that x times the standard deviation plus the mean, which will equal to negative 1.2816 times 4 plus 20. And that is going to give me 14.8736 minutes. So if a person finishes faster than 90% of the time, that means they finished their shopping in 14.87 minutes. And that makes complete sense. If the number you got was bigger than that number or bigger than 20 minutes, you'll know that you did something wrong and you have to rethink your question. So for example, if you use norm.s.inverse of 90%, then you're gonna get, let me compute it here, norm.s.inverse of 0.90%, you're gonna get 1.28. That is the z-score. To turn it into a number, you're gonna say the z-score times the standard deviation, which is 4. The z-score times the standard deviation 4 plus 20, which is the mean, and you're gonna get a number that is bigger than 20 minutes, which is the average, and that's why you know you did something wrong and you have to rethink that question again. So make sure that you are making sense of the numbers that you're computing. Question number 11. In a certain school, students are categorized by their preferred subjects and extracurricular activities. The table below provides the distribution. Suppose one student is randomly selected from the school. What is the probability of selecting a student who's passionate about sports? So we're going to see how many people are passionate about sports. We see, so sports is this column right here. We have a total of 60. So if we choose one person, what is the probability that he or she is going to be passionate about sports? That is selecting from the 60 people out of the 232. What is the probability of selecting a student who loves both science and art? So how many students love both science and art? That is 25 students. So 25 out of the 232. What is the probability of selecting a student who is into language given that they are not interested in sports? So the person is not interested in sports, which means we're going to compute everybody else but the people who are interested in sports. So that is our options. We can pick from those people because it is given to us that the person is not interested in sports, right? So everybody else except for the people who are interested in sports. So we're going to add 75, 52, and 45 together. So 75. So that is the total. That is going to be, so let me compute that, 172. So now what is the probability of selecting a student who's into language, given that they're not interested in sports? So that is everybody who's interested in language except for the ones in sports. So that is going to be that plus that plus that divided by 172. So it's going to be 30 plus 12 plus 15, which is going to be 57. So it's going to be 57 out of 172. That is the final answer because we are given that we're looking at everybody except for those people who are not interested in sports, which is 172 students. And then it says, what is the probability of selecting somebody who's into language? So the people who are into language and not interested in sports are 30 plus 12 plus 15, which is 57. So that is 57 people out of the total students of 172. Because we know the fact that we're excluding anybody who likes sports. What is the probability of selecting a student who is either a math lover, either a math lover or in drama, or means addition. So that is one thing that you need to understand. So now we're looking at math lovers and interested in drama. So I'm just going to erase that one. So here are the math lovers. And here are the students that are interested in drama. Notice how I highlighted the 12 twice. So make sure when you are computing, you're not double counting. You're not double counting. So in other words, you can add the totals. However, you need to exclude 112 because you're counting it twice in these totals. So make sure to exclude that 12. Or you can basically add 25 plus 18 plus 15 plus 12 plus 18 plus 15, so you don't double count the 12 again. So you could say 45 plus 70 minus 12 over the 232 total, which is going to give you 103 over 232. Or otherwise, you can add the ones that I circled just once. So don't use the totals if you're confused. What is the probability of selecting a student who's passionate about either drama or science? So now again, or, which means addition. And pay attention to double counting when you have addition in a contingency table. So we're looking for students who are passionate about drama and science. So here is the drama. And here is the science. Notice how 18 is highlighted twice. So in other words, you can highlight both and then you're going to add the numbers you highlighted just once or one time. So if you add 20 plus 22 plus 25 plus 12 plus 18 plus 15, you're going to get a total of 112, and that is, you're going to divide by the total, and that is the probability. So in other words, let me just write it down here. You could say basically 85 plus 45, and then you subtract 118 because you double counted that, and divide by 232. What is the probability of selecting a student who's into music given that they are also enthusiastic about science? So because we're looking at everybody who's enthusiastic about science, only that category, I'm just going to highlight the category of enthusiastic about science. In that category, how many people are enthusiastic about music or music lovers? That is 20. So I'm going to say 20 out of a total of 85, out of the total of the 85 enthusiasts about science, because I'm only looking at those people and excluding anybody else. Number 12, in a factory, the production of a specific type of light bulbs has a mean lifespan of 1,500 hours and a standard deviation of 100 hours. If a random sample of 50 light bulbs is selected for quality testing, determine if the sampling distribution would be normal. If it is, find the mean and the standard deviation. So this is a normal distribution. However, I have a sample of that normal distribution. So because of that fact, I know this is the distribution of sample means. So when we are dealing with the distribution of sample means, the distribution is going to be normal as long as your sample is greater than 30. So I'm going to say here the sample size is larger than 30, which means the distribution is normal. Or we have a normal distribution. The mean for the sample distribution of sample mean is the same as the population mean, which is 1,500 hours. The standard deviation is the population standard deviation divided by the square root of the sample size, which is 100 divided by square root of 50. And that is going to give you approximately 14.1421 hours as well. So that is the standard deviation and the mean. In a raffle, there are 300 instant win tickets worth $10 each, 150 tickets worth $50 each, and 20 tickets worth $200 each. $200 each. If 8,000 tickets are sold and each ticket costs $5, what is the expected value of this raffle? So I have a mistake on the key, so I will fix that. The first step in order to solve this question is basically to create the discrete probability distribution. So we have here the number of tickets available. That is, we have 300 instant win tickets, and their value is at $10 each, or worth $10 each. 150 tickets, and they are worth 50 each. And then finally we have 20 tickets worth $200 each. We're going to find the probability of getting a $10 or 50 or 200. It's going to depend on the number of tickets available. So we have 300 available out of the 8,000 tickets sold, which is going to give me 0.0375. And then we have 150 out of the 8,000, which is going to give me 0.01875. On the key, I forgot the zero. I added 1 0 here. And then the 20 out of the 8,000, the probability of selecting a $200 ticket is 0.0025. Now the expected value, we know that the expected value is the mean, which you can use some product, but I'm going to use it manually. So I'm going to say it is each x times the probability of that x. So 10 times the probability of 10 plus 50 times the probability of 50 plus 200 times the probability of 200. So basically I'm multiplying this row by that row, corresponding numbers, and then adding everything together. I'm going to do the math here. So this is going to be approximately, it is 1.81. I'm going to round to the nearest cent. So the expected value is $1.81. So if the ticket costs $5, you're basically losing $3 and about 19 cents, or 20 cents, you could say. $3.20 each time you buy a ticket, you risk losing $3.19 or 20 cents approximately. Question number 14. Use the spinner to find the probability listed below. The probability of 3, we have 1 3 out of the 12 numbers on display. What is the probability of selecting an even number? We have 1, 2, 3, 4, 5, 6 even numbers, so 6 out of 12. What is the probability of selecting an odd number or greater than 7? So the odd numbers are 1, 2, 3, 4, 5, 6. And then the numbers that are bigger than 7 are 8. So that is 7, 8, 9. So that is going to give me 9 out of 12. So I counted the red ones and then the highlighted green ones. So I'm not going to double count. So 1, 2, 3, 4, 5, 6, 7, 8, 9 total numbers that satisfy that category. Question number 15. Question number 15. In a survey conducted in New York City, it was found that only about 45% of residents have reusable shopping bags. A random survey of 12 New York City residents was taken, and the number of residents with reusable shopping bags were recorded. Explain how this scenario satisfies the 4 requirements for a binomial distribution. So I'm just going to say the conditions here. I don't want to write because it takes a lot of time to write it down. So first of all, we have a fixed number of trials because we selected a sample of 12 New York residents. So that is a fixed number of trials. So we're repeating this experiment 12 times. Each trial is independent of the other because we are distributing some surveys randomly. So these trials are independent of one another. One survey is not going to affect the other survey. 3, the two possible outcomes. This experiment has two possible outcomes. Either you're going to choose a person or a New York resident who uses reusable bags, that is success, or doesn't use a reusable bag or doesn't have a reusable bag, which is failure. Again, success and failure in binomial doesn't mean anything negative or anything positive in any way. The fourth condition, we have a constant probability of success, which is 45%. So the probability of success is the same for all trials, and that means it satisfies the 4 conditions. So we're done with the first part. Create a full binomial distribution table using Excel and write the table below. Round probabilities into 4 decimals. So what we need the number of trials, which is 12, and we need P, which is the probability of success, which is 45%. To do that on Excel, you're going to go on Excel on any sheet, and you're going to type X and then P of X. You don't need to type that, but just for the sake of making it nice, I'm going to do it. And then the trials are from 0 to 12. So 0, 1, 2, 3. I'm going to select all of that and then fill. I will go all the way until I have 12. Now to find the probabilities, I'm going to say I will use binomial distribution. Binomial.distribution is going to ask for numbers. So click on the 0 first, comma, the number of trials. I know the trials are 12. The probability is 0.45, and then we do not need to cumulate that, or we don't want to cumulate that, so I'm going to just say 0. So for the binomial, do not cumulate. For the normal distribution is the only time you need to cumulate. So now here is the first number. I'm going to populate. So I will select it and then go all the way down, and you can round that to 4 decimal places, just like I showed you. Then you're going to copy your data or table, and you're going to put it on your answer sheet. So the table should go here. Now, to answer the next question, what is the probability that at most 8 New York City residents have reusable shopping bags? That means either 8 or 7 or 6 or 5 or 3 or 5 or 4 or 3 or 0 residents have reusable bags, which means I will add the probabilities from 0 to 8. So I will just say this is equal to the sum of the probabilities from 0 to 8. And that is going to give me this answer. So I will write it down. The answer is about 96, 0.9644 or 96.44%. What is the mean number of New York City residents with reusable shopping bags? The mean for the binomial distribution, the mean for the binomial distribution X, so sometimes you see me say BI here to remind myself, is equal to N times P, which is 12 times 0.45, and that is going to give me 5.4 residents. What is the standard deviation? The standard deviation for the binomial distribution is the square root of N times P times 1 minus P, which is the square root of 12 times 0.45 times 1 minus 0.45. If you type it like that exactly on Excel, square root is SQRT, you're going to get an answer, or you could use a calculator, and that is going to give me 1.72 residents. Question number 16, last but not least. During the 2020-2021 flu season, 68% of children aged 6 months to 4 years got their flu shot. 59% of children aged 5 to 12 got their flu shot. 51% of children 13 to 17 got their flu shot. 38% of adults 18-49 got their flu shot. 54 of adults age 50-64 got flu shot. 75% of adults age 65 and up got their flu shot. If you randomly select one person from each age group, what is the probability that we get at least one person that got their flu shot? So in order to find the probability that we got at least one person who got their flu shot, we'll calculate the complementary probability of getting 0 people who got their flu shot in each age group and then multiply them together. So when you have at least in a specific setting like this one, it is best to use the complement event instead. So if let's denote that PC1 represents the probability that a child between the age of 6 months to 4 years old didn't get their flu shot, which means 1 minus the probability that they got their flu shot, 0.68, which will equal to 0.32. Let's say PC2 is the probability that a child aged 5 to 12 years old didn't get their flu shot, which means it's 1 minus their probability of getting the flu shot, which is 0.59, and this is going to be equal 0.41. Let's say PC3 is the probability that a child aged 13 to 17 years old didn't get their flu shot, which means 1 minus the probability that they got it, 0.51, and this is going to give me 0.49. Now we're going to move on to adults. So we're going to say PA1, let's say adults, EA is adults. That is the probability that an adult aged 18 to 49 years old didn't get their flu shot, which means 1 minus 0.38. 38 is the probability that they got it. So this is going to give me 0.62. And then the probability A2 is the probability that an adult aged between 50 and 64 years old didn't get their flu shot, which means 1 minus 0.54. And this is going to give me 0.46. And last but not least, the probability that PA3, probability that an adult age 65 and up didn't get their flu shot, which is 1 minus 0.75. And this is going to give me 0.25. So the probability that at least one person with flu shot is equal to 1 minus the probability that no one had flu shot, which will equal 1 minus probability no one had a flu shot is the probability of the first group of children didn't get flu shot, the second group of children didn't get a flu shot, the third group of children didn't get a flu shot, the first group of adults didn't get a flu shot, the second group of adults didn't get a flu shot, and the last group of adults didn't get a flu shot. In other words, it is P and minus PC1 times PC2 times PC3 times PA1 times PA2 times PA3, which equals 1 minus 0.32 times 0.41 times 0.49 times 0.62 times 0.46 times 0.25, which will be equal to 1 minus 0.0122. If you do the subtraction, you get approximately 0.9878, which is, or you can say 98.78%. So the probability that we get at least one person that got their flu shot is 98.78%. And that concludes the test review. I hope this helped.